Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us downward into the hidden heart of our planet, on a slow and steady descent through layers of stone and metal, heat and pressure, to imagine what's truly hiding 4,000 miles beneath our feet. We'll follow the unseen forces that shape the ground we walk on, the restless energy of the Earth itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly enjoy these quiet explorations. And when you're ready, perhaps leave a comment to tell me where in the world you're listening from and what time it is for you right now. It's always such a joy to see how these calm journeys connect us across continents, each of us in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's begin our journey. If your mind starts to wander at any point, that's perfectly fine. Let it drift. We'll still be here, unfolding the story at the same unhurried pace. The earth beneath you might seem still. Your room is quiet, the walls unmoving, the floor solid and dependable. But this calm is only the surface of things. Beneath it, our planet is in constant motion, not in the way of rushing rivers or blowing winds, but in a much slower, heavier dance. Whole continents shift and glide. Mountains rise grain by grain. Heat flows upward from the deep, while old, dense rock sinks back down into the mantle, starting the cycle over again. This restlessness is invisible to us in our daily lives, but it is always there, shaping the face of the world. The gentle curve of a hill, the jagged edge of a coastline, the sweep of a mountain range, all are written by the invisible hand of forces working far below. In a way, our planet is both a home and a machine. Not the kind built from gears and bolts, but one made from stone that can flow, metal that can swirl, and heat that can move mountains. If we could peel the earth open like a piece of fruit, we'd see its layers, not bright and colourful like slices of citrus, but vast shells of different materials, each with its own role to play. At the very surface lies the crust, astonishingly thin compared to the whole planet, like the skin of an apple. Beneath that, the mantle, a deep and slow-moving sea of rock. Then the outer core, molten metal swirling like an ocean under impossible pressure. And finally, at the centre, the inner core, a sphere of solid iron glowing hot in eternal darkness. We know these layers not by touching them. No one has ever been anywhere near that deep, but by listening. Seismology lets us hear the planet's structure. When earthquakes send vibrations through the Earth, those waves travel differently through solid and liquid, through dense and light materials. By recording them across the world, scientists can build a kind of echo map of the inside. It's a little like listening to the heartbeat of someone sleeping in the next room. You can't see them, but you can tell something about their size, their posture, their health. Every discovery about Earth's interior is a reminder that our surface is only a thin, fragile boundary. The ground we walk on is part of a slow, unending conversation between the surface and the depths, volcanoes bringing molten rock upward, subduction zones sending old seafloor back down, continents drifting apart and colliding again. Tonight, we'll explore that conversation, layer by layer. We'll move from the crust to the mantle, from the outer core to the inner, and then back to the surface again. We'll follow the journey of heat and rock, the creation of mountains, the rumble of earthquakes, and the flicker of auroras in the sky, all linked by the deep forces that keep our planet alive and changing. And as we travel, we'll remember, the Earth has been at this for billions of years, long before any human thought to measure it, and it will keep going long after we're gone. Its movements are patient, almost unnoticeable in a single lifetime, but powerful beyond measure over the long span of time. It is a reminder that change can be constant and still feel like stillness. So close your eyes if you'd like. Picture the ground beneath you not as a solid, unchanging thing, but as the outermost layer of something vast and alive. Imagine descending slowly, gently, through rock and heat, hearing the faint echoes of a living world beneath your feet. This is where our journey begins. No human has ever stood even halfway to the Earth's centre. The deepest we've managed is just a scratch compared to the hole, the Kola super-deep borehole in Russia, drilled over decades, reaching about 12 kilometres down. It is an impressive engineering achievement, yet on the scale of the Earth, it's like barely breaking through the paint on the surface of a door and trying to guess what lies in the rooms beyond. And so, most of what we know about the deep Earth doesn't come from seeing or touching it, but from listening. We listen to the way the planet moves and vibrates, to the way energy travels through it. Earthquakes, which we usually think of as destructive events, are also the planet's way of revealing its own secrets. When the crust shifts suddenly, it sends waves rippling through the entire body of the planet. These waves are not like the waves you see on water, but patterns of compression and bending that move through rock. Scientists call them seismic waves. There are two main kinds: P waves, which move by squeezing and stretching, and S waves, which move by shearing side to side. You don't need to remember the names, but the difference matters. P waves can travel through both solid and liquid, while S waves can only travel through solids. When an earthquake happens, sensors all around the world detect these waves, noting when they arrive, how strong they are, and what paths they've taken. The missing S waves on the far side of the planet after a quake tell us that somewhere deep inside there is a layer that must be liquid, the outer core. By collecting these signals from thousands of earthquakes over many years, scientists can create something like an ultrasound image of the planet, not sharp and colourful like medical scans, but a ghostly, shadowed map showing where material is denser or lighter, faster or slower to transmit vibration. This is how we discovered features with names that sound mysterious even before you know what they are. Mantle plumes, subducted slabs, and ultra-low velocity zones, places where seismic waves slow dramatically, hinting at pockets of molten or unusual rock. It is remarkable that we can know these things without a single human ever setting foot there. In a way, this is how much of science works, piecing together the unseen from the patterns we can detect. You might compare it to listening to music through a wall. You can't see the instruments or the musicians, but you can tell if the notes are bright or deep, fast or slow, and you can imagine the shape of the song. There are other ways we listen to the Earth as well. The planet has a magnetic field generated by the motion of molten metal in its outer core. By carefully mapping the strength and direction of this field, we can find subtle changes that hint at what's happening far below. Some of these patterns shift slowly over decades. Others have been etched into rock for millions of years, like ancient recordings of the planet's behaviour. Gravity, too, speaks to us about the deep interior. The pull you feel standing on the surface is not perfectly uniform everywhere. Slight differences in rock density below can make gravity very slightly stronger or weaker in different locations. Satellites can measure these changes, giving us another layer of the puzzle. Over time, these measurements have revealed where huge slabs of old seafloor have sunk deep into the mantle, and where hot columns of rising rock are pushing upward toward the crust. Taken together, the seismic waves, the magnetic variations, the subtle shifts in gravity, these are the ways we learn without touching. They are the faint traces left on the surface by movements thousands of miles below. From them we build models, and from those models we tell stories of how the Earth came to be as it is today. And like all stories, the picture is never complete. Each earthquake, each new magnetic survey, each satellite pass adds another detail, sometimes confirming what we thought we knew, sometimes changing it entirely. In that way, the deep Earth is a little like the night sky. Even if you've looked up 1,000 times, there is always more to notice, more to understand if you watch closely enough. This is the quiet joy of studying something you cannot see directly. It requires patience, imagination, and the willingness to accept that you will never hold the whole picture in your hands. The Earth will always keep some of its secrets, but perhaps that's part of why it feels alive. Not just because it moves, but because it holds something back, like a friend who tells you only some of their dreams, leaving the rest to your curiosity. And so, as we continue our journey inward, we carry with us not a set of complete instructions, but a map drawn in whispers and hints. We will follow those hints into the next layers, moving deeper into the mantle, where heat and pressure begin to change rock into something almost like a living current. But before we go there, it's worth remembering that everything we're about to imagine, every picture in our mind of that hidden world, is built from the faintest signals, patiently collected and carefully interpreted. We are, in a sense, listening to the Earth's slow, deep voice and learning to understand its language. When we piece together all the ways the Earth speaks to us, the tremors that circle the globe, the gentle tug of gravity, the shifting lines of its magnetic field, we begin to see a kind of map. It is not the sort of map you could roll out on a table or hang on a wall. It has no sharp coastlines or neat labels, no bright blue for the seas or green for the forests. It is more like a shadowed sketch, blurred at the edges, where what's missing is as telling as what's shown. These maps are made not of colour, but of speed. They tell us where seismic waves hurry through dense rock and where they slow, stumbling through molten or partially melted zones. They tell us where cold slabs of old seafloor have sunk deep into the mantle, and where hot plumes of rising material are pressing upward, ready to become volcanoes at the surface. It is a map of temperatures, densities, and hidden movements, a kind of pulse chart for the entire planet. In these images, taken from the patient listening of thousands of sensors over years, we can trace the shapes of things we will never see with our own eyes. A mantle plume is not something you could point to directly, but in the data it appears like a ghostly column, stretching from the deep mantle up toward the crust, carrying heat and molten rock. Subducted slabs, on the other hand, show us cooler, faster regions, relics of ancient ocean floors pulled downward and slowly disappearing into the hot depths. Sometimes these maps reveal something stranger, ultra-low velocity zones, or ULVZs, lying just above the boundary between the mantle and the outer core. In the language of seismic data, these are places where waves suddenly slow to a crawl. In the language of imagination, they are like patches of thick fog at the bottom of a dark valley. You can't tell exactly what they are, only that something unusual lies there. Some scientists think they might be pools of partially melted rock, perhaps mixed with material from the core itself. Others suggest they could be ancient crust that sank billions of years ago, preserved at the edge of the Earth's deepest sea. Even without knowing exactly what they are, the presence of these features changes the way we think about the deep Earth. It is not a uniform, perfectly layered sphere. It is complex, varied and textured, a place with mountains and valleys of its own, made not of stone we can walk on, but of forces we can only feel at a distance. These subtle structures have consequences for life on the surface, even if we never notice them directly. A mantle plume can feed a volcanic hotspot for millions of years, building islands in the middle of oceans like the Hawaiian chain. A subducted slab can trigger earthquakes half a world away from where it began. Even the great currents in the mantle, shifting hot material upward and pulling cooler rock downward, help control the movement of tectonic plates, which in turn shape our continents, our seas, and even the climate over geological time. If you try to picture the mantle from these maps, you might imagine something between a slow ocean and a drifting cloud bank. In places there are broad flows of warm rising material, in others narrow streams of cooler sinking rock. These flows are not hurried. They take millions of years to travel from one layer to another, but over time they move enough mass to remake the surface entirely. Where two upward flows meet, the crust may bulge, lifting mountains or spreading apart to form new ocean. Where a downward flow pulls, the crust may sag or crack, inviting the deep to come closer to the surface. This is the beauty of these whispered maps. They show us that Earth is not frozen, but alive with motion, even in the places we call solid. The crust is a raft, the mantle a slow tide, the core a great hidden engine driving it all. And while the data that create these maps come from instruments and algorithms, there is something strangely human about the process. We're trying to understand a place we can never visit, using clues that arrive in waves and fragments. It is a kind of distant relationship, the kind where you piece together someone's inner life from the way they speak, the pauses they take, the glances you catch from across the room. Scientists continue to refine these maps, adding detail with every new earthquake recorded, every magnetic survey completed, every gravity measurement taken from orbit. Each refinement is a step toward clarity, yet also a reminder that complete certainty is impossible. The Earth's interior is not a static place waiting to be fully charted. It is changing as we study it, shifting in ways so slow we can only sense them when we compare one generation's map to another's. And so these maps are less like final portraits and more like ongoing sketches, outlines drawn in pencil, with some lines dark and confident, others faint and tentative, waiting for the next discovery to bring them into focus. They remind us that science is not just about having the answers, but about being willing to live with the partial picture, to keep asking questions even when we know we will never see everything directly. As we leave these shadowy maps behind, we will begin to move through them, at least in our imagination. We will step from the crust into the mantle, the slow-moving sea of rock that carries heat and shapes the continents. We will imagine its texture, its temperature, and its quiet power. And though our journey is only in thought, the truths we follow are real, carried upward to us in the patient signals the Earth has been sending all along. When you imagine the Earth, it's easy to think of it as entirely solid, one vast, immovable sphere of rock. Yet the part we live on, the part we see, is only the very outer layer, astonishingly thin compared to the whole. If the planet were the size of an apple, this crust would be no thicker than the fruit's skin. And like the skin of an apple, it's easily broken, scarred, and reshaped. It's on this skin that every river flows, every forest grows, every city stands. It's where mountains are built, where oceans rest, where all of human history has unfolded. And yet, for all its importance to us, this layer is not fixed. It is divided into enormous pieces called tectonic plates, and these plates are not stationary. They drift slowly but steadily across the surface of the planet. Imagine them as rafts on a vast invisible lake, a lake of rock so hot and dense that it can flow over millions of years. The plates float upon this deeper layer carried by currents of heat rising from the mantle below. You could watch them for an hour, a day, or a year, and you would see nothing change. But over centuries, over millennia, the movement becomes clear. Where these plates meet, the world is often restless. In some places they push together, crumpling the crust into mountains. This is how the Himalayas are still growing today, rising by a fraction of an inch each year as the Indian plate presses into the Eurasian plate. Stand in those mountains and you're standing in the middle of an ongoing collision, one so slow you could live your whole life there without noticing, yet powerful enough to raise the tallest peaks on Earth. In other places, the plates slide past one another, their edges grinding and catching. The San Andreas Fault in California is one such seam. Most of the time, it is silent, its movement too small to feel. But when enough pressure builds, the rocks can slip suddenly, sending shock waves racing through the crust. It is the stillness between these slips that makes the fault seem quiet, the quiet of a breath being held for years. Elsewhere, plates move apart, opening long cracks in the ocean floor. From these cracks, molten rock rises to create new crust, pushing the plates further apart. This is happening right now along the mid-Atlantic ridge, a mountain range under the sea that runs for thousands of miles. Every year the Atlantic Ocean grows just a little wider because of it, though you'd never notice without precise measurements. The crust is not uniform. In some places, under the oceans, it's only a few miles thick. In others, beneath mountain ranges, it can be more than 40 kilometers deep. But whether thick or thin, it's all vulnerable to the slow forces below. The mantle moves, and the crust responds, sometimes by bending, sometimes by breaking, sometimes by carrying whole continents across the face of the planet. It can be humbling to realize that the ground beneath us is not as permanent as it feels. We're used to thinking of land as stable, the foundation for everything else, and in human terms it is. Roads, buildings, and forests stand for decades or centuries without seeing the plates shift more than a few inches. But in geological terms, the crust is a restless shell, moving in ways that will redraw coastlines and mountain ranges over deep time. This movement has been going on for hundreds of millions of years. Continents have joined together and broken apart more than once. The supercontinent Pangaea existed long before the first humans, before even the first dinosaurs. It split apart, sending the land masses drifting into the shapes we recognize today. And just as they have drifted before, they will drift again, until new continents are formed in the distant future. The crust may be thin, but it is the interface between two worlds, the dynamic interior and the living surface. It is shaped from below by the push and pull of the mantle, and from above by wind, water, and ice. Over millions of years, mountains rise and are worn down, valleys deepen and fill, oceans open and close, and through it all, the crust remains the fragile stage upon which the story of life unfolds. Standing here, on this thin shell, it's almost impossible to feel its movement. But the signs are there, if you know where to look. In the slow uplift of a mountain range, in the long straight line of a fault cutting across a landscape, in the symmetrical pattern of ridges and valleys on the ocean floor. Each is a reminder that the crust is not fixed. It is a living boundary, shaped by forces far older and stronger than we are. As we begin to move downward from the crust into the mantle, we leave behind the layer we know best. The familiar world of soil and stone, of landscapes and landmarks, gives way to something stranger. A realm where rock is still solid but can flow, where heat is the main driver, and where the surface's slow drifting begins. It is there, in the mantle, that the story of the crust motion truly begins. If the crust is the skin of the world, then the mantle beneath it is something like the flesh, thicker by far and endlessly more mysterious. We cannot see it, and we cannot touch it, yet it makes up most of the planet's volume. It lies below every continent, beneath every ocean, a vast and hidden expanse of rock. And though the word rock may sound solid and still, the mantle is anything but static. The mantle is solid in the sense that you could not swim through it, nor fall through it as if it were water, but under the immense heat and pressure of the deep earth, even rock can flow given enough time. This flow is not quick. If you could watch the mantle in motion, you might see a pace so slow it would seem frozen to the eye. Yet over millions of years, the movement becomes as undeniable as the tide. Heat is what makes this possible. Deep within the earth, heat is constantly being released. Some left over from the planet's formation, some from the decay of radioactive elements, and some from the slow solidification of the inner core. This heat rises through the mantle, and as it does, it causes parts of the rock to become less dense and more buoyant, just enough to drift upward. In other regions, cooler, denser rock sinks down to replace what has risen. It is a slow but steady circulation, like the currents in a pot of thick soup left simmering on the stove. Scientists call this process convection, but you can think of it as a kind of breathing. The mantle breathes heat outward, and with that breath, It carries the materials that shape the surface above. Where rising currents push against the crust, continents are lifted and volcanic activity may follow. Where sinking currents pull downward, trenches form and slabs of crust are drawn deep into the earth to be melted and remade. This cycle has been running for billions of years. Old ocean floors sink into the mantle, their minerals recycled into the deeper layers. From that same mantle, new magma rises to create fresh crust at mid-ocean ridges, spreading the sea floor like a slow-moving seam. In this way, the surface of the Earth is constantly renewed, not in the span of human lives, but on the scale of geological time. It is in the mantle that the birthplaces of magma lie. Here, heat and pressure coax solid rock into a partially molten state, forming pockets of material ready to rise through cracks and weaknesses in the crust. Some of this magma will feed quiet volcanic flows, building new land grain by grain. Some will erupt violently, altering the landscape in a single day. The type of volcano, the minerals in its lava, the gases it releases, all are influenced by the nature of the mantle below. The mantle also plays a quiet but essential role in Earth's long-term climate. Over millions of years, volcanic activity, driven by mantle processes, releases carbon dioxide into the atmosphere. Weathering of rock on the surface, itself connected to the rise and fall of mountains, removes that carbon again. It is a balance the planet has kept for eons, one reason why Earth has remained hospitable to life, when other worlds have not. You could imagine the mantle as a slow river, flowing not in a channel but through the very body of the Earth. It does not have banks or surface ripples, but it does have currents, eddies, and vast looping paths. Some of these currents rise from deep in the lower mantle, perhaps even from near the core mantle boundary, while others circulate within the upper mantle alone. Together they connect the deep earth to the surface in a web of motion that never truly stops. In the language of science, these patterns can be mapped with seismic tomography, showing whether rock moves faster or slower. In the language of imagination, the mantle is an ocean in permanent twilight. No surface, no shore, just heat and movement in the dark. Rising plumes might be like slow columns of smoke, drifting upward for thousands of miles. Sinking slabs might be like ancient ships, heavy and cold, slipping into the depths without a sound. And while the mantle seems vast and unchanging, it is shaped by history. Some of its materials have been there since the Earth formed. Others are recycled from crust that once lay under ancient seas. When you hold a piece of basalt or granite, you may be holding rock that has been to the deep mantle and back again, part of a cycle so long it defies our sense of time. If the crust is where the story of life is told, the mantle is the slow author, writing in a script we cannot read directly, but can feel in the mountains, the valleys, the shifting lines of the continents. It is here, in this slow river of rock, that the surface gains its shape and its restlessness. As we continue downward, we leave behind the partially molten pockets and slow-moving currents of the mantle's upper layers. We will soon reach the boundary where the rock gives way to something stranger, a vast ocean not of water, but of molten metal, churning and swirling in the darkness. It is here, in the outer core, that the Earth's protective magnetic field is born. Beneath the mantle, far deeper than any place where rock can still hold its shape, lies a boundary as profound as the surface of an unseen sea. Above it, the mantle moves like a slow river of stone. Below it, the rock is gone, replaced by something stranger, an ocean of molten metal swirling in darkness under pressures we can scarcely imagine. This is the outer core, and it is unlike anything else in the Earth. It is a vast sphere of liquid iron and nickel, perhaps mixed with lighter elements, stretching from about 1,800 miles beneath your feet down to the very centre of the planet's heart. If you could stand there, though of course you never could, you would be surrounded by heat close to 4,000 or even 5,000 degrees Celsius, and by a fluid so dense it would feel like swimming in molten steel. The outer core moves constantly, its currents driven by two main forces, the heat rising from the deeper inner core and the cooling that happens as material in the outer core slowly solidifies onto the inner one. The molten metal circulates in great looping patterns, spiraling and churning under the influence of Earth's rotation. These motions are not random. They have a rhythm, a structure, like the great gyres of the oceans on the surface. Only here the water is liquid iron, and the currents are tens of thousands of miles around. It is these movements that create one of Earth's most vital features, its magnetic field. As the molten metal flows, it generates electric currents, and those currents in turn produce a magnetic field that wraps around the planet. This process is called the geodynamo, and without it, life on Earth might never have been possible. The magnetic field extends far into space, forming a shield called the magnetosphere. It deflects much of the solar wind, the stream of charged particles constantly flowing from the sun. Without this shield, the solar wind would strip away Earth's atmosphere over time, much as it has on Mars. With it, our air remains thick enough to breathe, our oceans deep enough to cradle life, and our surface safe from most of the sun's harsher radiation. We rarely think about the magnetic field, but we see its beauty in the shimmering curtains of the auroras. These lights are born when some of the charged particles from the sun slip past the shield near the poles and collide with our atmosphere, making it glow in green, pink, and violet veils. The next time you see an image of the northern or southern lights, you are seeing the outer core's work made visible, a display painted in the sky by the churning of molten iron, thousands of miles below. The outer core is not static. Its flows can shift, and with them, the magnetic field can wander. Over the centuries, the magnetic North Pole has moved across the Arctic, sometimes slowly, sometimes faster, and occasionally the field reverses entirely. North becomes south, south becomes north. These magnetic reversals do not happen on a human schedule. They take thousands of years to complete and may occur hundreds of thousands of years apart. The last full reversal was about 780,000 years ago. We don't yet know exactly why they happen, only that they are part of the outer core's slow and deliberate dance. If you imagine the outer core in motion, it's worth picturing something graceful rather than chaotic. Think of it like a vast, deep ocean in perpetual twilight, stirred by invisible tides. Columns of molten metal rise and fall, curling into spirals under the Coriolis effect of the planet's spin. Each turn of those currents is a stroke in the painting of our magnetic shield, a design that shifts so slowly we only notice its changes when we look across centuries. The scale of this place is difficult to hold in the mind. The outer core is more than 2,000 kilometers thick, thicker than the radius of the moon. It contains enough liquid metal to fill all of Earth's oceans many times over, and every ounce of it is in motion, its energy drawn from the deep heat of the planet's heart. Without the outer core, Earth would be a different world entirely. Its surface might still have mountains and oceans, but it would be exposed to the unfiltered force of the sun. Over time, the air might be stripped away, the seas evaporated, and life as we know it gone. This ocean of metal is not just a feature of the Earth's interior. It is a guardian, silently shaping the conditions in which we live. And yet, like the rest of the planet's deep interior, it remains beyond our reach. We cannot drill to it. We cannot sample it directly. We know it through the same indirect whispers we followed from the crust downward, the way seismic waves slow as they enter it, the absence of S-waves that cannot pass through liquids, the behavior of the magnetic field it generates. All of these together tell us that far below the mantle lies this molten heart ocean, unseen but essential. As we continue deeper, we will reach the boundary where this liquid sea ends, and something even stranger begins. A solid sphere suspended in the very centre, blazing with heat yet locked in place by unimaginable pressure. This is the inner core, the still heart of iron at the centre of the Earth. At the very centre of the Earth, beyond the drifting crust, the slow mantle, and the swirling ocean of molten metal lies something unexpected. It is not another sea, not another current, but a sphere of solid iron and nickel, suspended in the deepest darkness. This is the inner core, the still heart of the planet locked in, placed by pressures so immense that even at temperatures as hot as the sun's surface, the metal cannot melt. It is a paradoxical place, blazing hot yet solid, immovable yet slowly growing. Around it the outer core churns and flows, but here there is no current, no convection. It is as if the heart of the Earth has chosen a different rhythm, one of stillness, endurance, and quiet heat. The inner core is about 1,220 kilometers across, a little smaller than the Moon. It is made mostly of iron, with a touch of nickel and perhaps lighter elements, all packed so tightly together that a single cubic meter would weigh more than 13,000 kilograms. It is hard to picture such density in human terms, but you might imagine taking a mountain and pressing it down until it fits inside a single city block. That is the kind of compression we are speaking of here. This immense pressure is what keeps the inner core solid, even though the temperatures are estimated at around 5,000 to 6,000 degrees Celsius. Without that pressure, the metal would be liquid just like the outer core. But here, at the centre, gravity's grip is absolute. Every atom is locked in place, pressed from all sides by the weight of the planet above it. And yet, the inner core is not entirely frozen in time. It is slowly growing as heat escapes from the deep earth and the molten metal of the outer core solidifies onto its surface. This growth releases latent heat, the energy that was stored in the molten state, and that heat continues to drive the convection currents in the outer core. In this way, the still heart of iron feeds the restless ocean around it, sustaining the magnetic field that shields our world. Some studies suggest that the inner core might not be perfectly uniform. Seismic waves passing through it sometimes travel at slightly different speeds, depending on their direction, hinting at patterns in the crystal structure of the iron. Others suggest that there might even be an inner core, a smaller sphere within the sphere, with its own distinct orientation. If true, this would mean that the centre of the Earth has layers within layers, like a Russian nesting doll made entirely of metal and heat. In the language of science, the inner core is a solid phase of mostly iron, crystallizing under extreme conditions. In the language of imagination, it is a glowing ember held in eternal darkness, a light that never reaches the surface, but whose warmth keeps the whole planet alive. We will never see the inner core directly. No drill could survive the journey, no human could withstand the pressure. Even our most detailed knowledge comes from the same method we've used all along, listening to how seismic waves pass through it. When waves from powerful earthquakes travel through the planet, some pass directly through the inner core, and by measuring their speed and direction, we can infer its size, density, and composition. It is a kind of echolocation on a planetary scale. The inner core's existence reminds us of how much we live by inference, how much of our understanding of the world comes not from direct sight, but from the careful reading of signs. We cannot stand at the centre of the Earth, yet we can say with confidence that it is there, that it is solid, that it grows, and that it plays a vital role in keeping the rest of the planet's systems running. And though it is unimaginably far below us, the inner core touches our lives every day. Without it, the geodynamo in the outer core would weaken, the magnetic field would fade, and the solar wind would begin to erode our atmosphere. The Earth would slowly become less hospitable, less protected. The stillness at the centre is not passive. It is the foundation for the motion and life above. If you close your eyes and imagine the descent, you might picture passing through layers that grow darker and hotter with each mile until you finally arrive at this central sphere. It would not be glowing in open light. There is no air, no space for a flame. But you might sense a fierce heat pressing in from all sides, a kind of steady pulse in the darkness. You might feel, rather than see, the weight of the entire planet gathered above you, and in that place there would be no sound, no wind, no movement, only the dense, silent presence of the Earth's heart. From here, there is nowhere deeper to go. The inner core is the end of the journey inward, the last page of the Earth's hidden book. And yet, it is also a beginning, the place from which the planet's heat flows, the place whose quiet endurance sustains the restless layers above. From this central stillness, our path will turn outward again. We will cross invisible borders where one layer becomes another, places where seismic waves change speed, where the nature of matter shifts. These boundaries, the moho, the D double prime layer, are as important to the story as the layers themselves. They are the shorelines of the Earth's inner oceans, and they hold clues to the planet's past. The journey through Earth's interior is not just a passage through layers, but through boundaries, invisible places where one kind of world gives way to another. You cannot touch these borders. You cannot see them in any photograph. And yet, their presence is as real as the surface we stand on. Each boundary is marked not by a visible line, but by a sudden change in the way seismic waves travel, in the way density shifts, in the way temperature and composition alter the behavior of the material. These changes are often sharp, like the edge of a cliff, but they are revealed to us only in the numbers and patterns of our measurements. The most famous of these is called the Mohorovičić discontinuity, or simply the MOHO. It is named for the Croatian seismologist Andrija Mohorovičić, who in 1909 noticed that seismic waves from an earthquake moved faster once they reached a certain depth. The simplest explanation was that they had entered a denser layer, the mantle, from the less dense crust above. The moho is the shoreline where the crust meets the vast, slow-moving ocean of the mantle. It lies, on average, about 35 kilometres below continents, and only about 7 kilometres beneath ocean floors. Above it is the crust we know, fractured and weathered by surface processes. Below it is the mantle, where rock exists under pressures and temperatures that begin to change how it behaves. Though we will never see the moho directly, we live our whole lives above it, as if walking along a bridge over a hidden sea. Far deeper lies another mysterious border, the double prime layer, just above the core mantle boundary, roughly 2,700 kilometres below the surface. It's a place where seismic waves behave strangely, slowing or bending in ways that suggest changes in temperature, composition, or both. Some scientists believe the D double prime layer may be where ancient slabs of crust, subducted billions of years ago, now rest in a kind of deep graveyard, slowly mixing with the mantle around them. Others think it might be a region of partial melt, where rising heat from the outer core begins to soften the rock above. If the moho is a shoreline, the D double prime layer is a deep, shadowed trench at the bottom of an ocean, a place where currents meet, where strange things accumulate, and where the rules of the surface no longer apply. These borders are not static. Over millions of years they can shift, their depth changing as the dynamics of the mantle evolve. A rising plume of hot rock might push the D double prime layer upward in one place, while the slow sinking of a cold slab might drag it deeper in another. Even the moho, which feels fixed in human terms, is part of the crust's long conversation with the mantle below. The importance of these boundaries is not only in what they mark, but in what they tell us about Earth's history. The very fact that the moho exists shows that the crust and mantle have distinct compositions, forged in the planet's earliest days when lighter materials floated upward and heavier ones sank. The D double prime layer, meanwhile, may preserve relics from those same early times, buried so deep that surface processes could never reach them. Studying it is like reading the oldest surviving chapter of the planet's story, one written in a language we are still learning to decipher. We sense these borders in other ways too. The outer core's magnetic field does not pass through the mantle unchanged. The mantle conducts and guides it, and the nature of that guidance may be influenced by the d double prime layer. Earthquakes that pass through the moho send back echoes that help us refine our models of the crust. And in the rare, massive quakes that send waves all the way through the core, we catch glimpses of the deep boundaries by how those waves bend and scatter. To imagine these invisible layers, it helps to think not in terms of walls or fences, but of horizons. A horizon is not a physical barrier. It is a place where your view changes, where what lies beyond is hidden until you move toward it. The moho and the d double prime are like horizons in the deep earth. They are not edges you could touch, but transitions that change the nature of everything above and below them. If we could descend in person, we might notice nothing as we crossed them. There would be no sudden light, no shift in texture underfoot, only a gradual awareness, felt perhaps in the weight of the air if there were air at such depths, that something fundamental had changed. The atoms would be packed a little tighter. The rock would carry sound a little faster or slower. The rules would be just slightly different. These borders remind us that the Earth's interior is not a simple set of layers stacked neatly like a cake. It is a dynamic, evolving system where boundaries form, shift, and sometimes dissolve. They are records of movement, of transformation, of the endless conversation between heat, pressure, and time. From here, our journey will turn outward again. We have reached the deepest solid places and touched the edges between them. Now we will climb back toward the surface, tracing how these deep processes create the events we feel and see. Volcanoes rising, earthquakes rumbling, continents drifting under our feet. In leaving the deep earth, we carry with us its lessons, that even the most hidden places leave their mark on the world above. From the stillness of the inner core and the shadowed borders of the deep mantle, our path upward returns us to a layer whose motions we can see, not directly, but in the shape of the world around us. Here, at the surface, the continents themselves are moving, not with the rush of a wind or the crash of a wave, but with a pace so unhurried that a lifetime passes without any visible change. And yet, over millions of years, these movements become a kind of dance, slow and graceful in its own strange way. The continents are carried on tectonic plates, great slabs of the crust and uppermost mantle, that drift on the softer layer beneath. Their motion is driven by the slow convection currents of the mantle, the same currents we imagined as a simmering pot or a slow-breathing tide. Each plate moves only a few centimeters per year, but the journey is constant. Over time, these movements bring continents together and tear them apart, build mountains and open oceans. Scientists describe 3 main ways that plates meet, and each has its own rhythm. At divergent boundaries, the plates drift apart. This is the quiet opening of space, like partners stepping away from each other on a vast floor. Along the mid-Atlantic ridge, deep under the ocean, molten rock rises to fill the gap as the plates separate, creating new sea floor. The process is steady, almost serene. Each year the Atlantic Ocean grows by a few centimeters, a widening so small you'd never feel it, yet so steady that over millions of years it has turned a single ocean into 2, with continents drifting to opposite shores. At convergent boundaries, the plates move toward one another. Here, the dance becomes more forceful. One plate may crumple against another, lifting mountains higher, as in the collision that created the Himalayas, or one may sink beneath the other, sliding down into the mantle in a process called subduction. This is a slow, deep bow, one plate bending under the weight of the other. But it's also a meeting that can be violent, triggering earthquakes and feeding volcanoes along the boundary. Much of the Pacific Rim is marked by such boundaries, forming what we call the Ring of Fire, where earthquakes and eruptions are part of the natural rhythm. The third type, transform boundaries, are perhaps the most deceptive. Here, the plates slide past one another horizontally, their edges lock together until the stress is too much. Then they slip suddenly, releasing energy in the form of earthquakes. The San Andreas Fault is one of the most famous of these, a line across California where the Pacific Plate and the North American Plate move in opposite directions. For years, the movement is invisible, the fault quiet. Then, without warning, it shifts, and the ground above it feels the deep motion all at once. These three types of boundaries are the steps of Earth's continental dance. They happen slowly, yet their effects are written into the landscapes we know. Every mountain range, every ocean basin, every fault line is a trace of these movements. The continents you see on a map are not fixed pieces of a puzzle. They are travellers, caught mid-step in a journey that began billions of years ago and will continue for billions more. It is strange to think that the ground beneath us is not truly still. Even the rocks of ancient mountain ranges have stories of travel written in them. Minerals that formed under different pressures, fossils of marine life found high above sea level. They are reminders that land can rise from the ocean, that seas can split continents, that no place is forever as it is now. The slow dance of the continents shapes life as well as land. The joining or separation of land masses changes ocean currents, which in turn alter climate. It can create land bridges that allow species to migrate, or isolate them until they evolve into something entirely new. It is a dance that sets the stage for the story of life on Earth, changing the scenery with each step. In human time, these motions are almost imperceptible. We see only hints: the occasional earthquake, the slow rise of a coast, the drifting of an island a few centimetres from where it was last year. But in geological time, the movements are relentless. The continents have gathered into supercontinents before, Pangaea, Rodinia, Gondwana, and they will gather again. In about 250 million years, the plates may once more bring all the land together into a single mass, and the dance will start a new pattern. If you imagine the continents as dancers, they are not guided by music we can hear, but by the deep, slow beat of the planet's interior. Their steps are shaped by the heat rising from the core, by the pull of subducting slabs, by the rotation of the Earth itself. It is a choreography that began before life appeared and will continue long after we are gone. To watch it, you would need a timescale far longer than a human life. A camera set to capture each frame not every second, but every 1,000 years. Only then would the movement appear, continents drifting like ice on a slow current, colliding, sliding apart and colliding again. It is a performance with no finale, only cycles, each one carving and reshaping the world anew. As we continue our journey, we will step closer to the moments when the dance becomes something we can feel in an instant, when the slow build of pressure or heat is released in a sudden movement. In the next part, we will listen for the footsteps of the deep, the earthquakes that remind us that the Earth's slow motions are never entirely silent. For most of the time, the Earth's movements are too slow for us to notice. The continents glide apart or push together at a pace that feels like stillness. But every so often, the planet takes a step we can feel, a sudden shift, a jolt that travels through the ground and up into the world we know. These are earthquakes, the quick, startling footsteps of the deep. An earthquake begins quietly, deep along the fractures where tectonic plates meet or slide past each other. Stress builds as the rocks press together. They bend and strain, storing energy the way a branch might bend in the wind. For years, even centuries, this tension can grow with no sign at the surface. And then, in an instant, the rocks break or slip, releasing all that stored energy in a burst of motion. That motion radiates outward as seismic waves, ripples of energy that travel through the crust and mantle. Some are fast and sharp, racing ahead like a shout in a quiet room. Others roll more slowly like the sway of a heavy curtain. Together they can shake the ground for seconds or even minutes, toppling buildings, splitting roads, and moving the landscape by feet or yards in a single breath of time. In March of 2011, Japan felt one of these footsteps, the Tohoku earthquake. It struck off the country's northeastern coast, where the Pacific plate is subducting beneath the North American plate. The quake was massive, magnitude 9.0, and it shifted the seafloor by as much as 50 meters in places. The motion displaced enormous volumes of water, sending a tsunami toward shore. In a matter of minutes, entire towns were swept away, and the coastline itself was altered. The energy released was so great that it slightly shifted Earth's axis and shortened the length of the day by fractions of a second. Half a century earlier, in 1960, the most powerful earthquake ever recorded struck southern Chile. It measured magnitude 9.5 and lasted for more than 10 minutes, an almost unimaginable duration for the ground to keep moving. The rupture stretched for hundreds of kilometers along the coast, and the resulting tsunami crossed the Pacific, reaching as far as Hawaii and Japan. In that single event, the boundary between the Nazca and South American plates shifted in a way that will not be repeated in the same spot for centuries. Earthquakes can also strike in unexpected places, far from the familiar edges of tectonic plates. In New Zealand, the 2010 and 2011 Canterbury quakes occurred on faults hidden beneath farmland and city streets. The first caused damage but spared most lives. The second, smaller in magnitude, struck directly beneath Christchurch, collapsing buildings and claiming hundreds of lives. Here, the deep step of the earth was not only sudden, but heartbreakingly close to home. Not all earthquakes are catastrophic. Many are too small to feel, detected only by sensitive instruments. Yet even these minor tremors are part of the same system, reminders that the crust is constantly shifting, adjusting to the forces from below. In Alaska, the footsteps of the deep take a different form. As the massive ice sheets of the last ice age melted away thousands of years ago, the weight pressing down on the land lessened. Slowly, the crust began to rebound, rising back toward its original position. This process is still happening today. In some places, the land lifts by more than a centimetre each year, a slow-motion earthquake unfolding not in seconds but over centuries. You could think of it as the land itself taking a deep, slow breath after being pressed down for an age. For those who experience them, earthquakes can be moments of pure fear, the sudden loss of trust in the ground beneath your feet. But they are also part of the Earth's natural rhythm. They are the sound of tectonic plates adjusting, of faults relieving their tension, of the planet reshaping itself in ways that may not be visible for centuries, but are felt in a moment. Seismology, the study of these events, gives us ways to listen to the Earth's footsteps, even when they are too faint to feel. By tracking how seismic waves travel, we can map the hidden structures of the crust and mantle. We can learn where stress is building, where the next step might come, and how the deep movements connect across continents and oceans. Yet for all we know, prediction remains elusive. We can identify regions where large quakes are likely over decades or centuries, but we cannot yet say exactly when or where the next great release of energy will happen. In this, the Earth keeps its own time, and we are simply along for the ride. If you imagine standing in a silent room and hearing a single distant footstep, you might feel a shiver of curiosity. Who is moving? And where? Earthquakes are like that, except the sound is felt through the soles of your feet, through the walls, through the very air. They are the moments when the slow dance of the continents turns into something we can sense directly, a reminder that the planet's story is still being written beneath us. From here, our journey will turn to the fire that sometimes follows these footsteps, the molten rock that rises from the mantle, building mountains and reshaping landscapes in its own time. In the next part, we will stand at the edge of the hidden furnace and see how volcanoes connect the deep earth to the open sky. After the jolt of an earthquake, the earth sometimes speaks in a different voice. Instead of a single sharp movement, it opens a path from deep within, letting molten rock rise to the surface. Volcanoes are the places where this happens, vents in the planet's crust, where the slow heat of the mantle finds its way upward and bursts into view. They are the open chimneys of the hidden furnace, connecting the deep earth to the air we breathe. Not all volcanoes are the same. Some sit quietly for years or centuries, their summits capped with snow, their slopes green with forests or dotted with towns. Others are restless, their craters steaming, their flanks warm even in winter. And then there are those that seem almost alive in their activity, like Nyiragongo in the Democratic Republic of Congo. Nyiragongo is one of the most remarkable volcanoes on Earth, home to a persistent lava lake that can reach temperatures of around 800 degrees Celsius. From a distance, it can appear deceptively calm, a faint orange glow above the crater at night. But stand at the rim, if you could, and you would see a vast, roiling surface of molten rock, breaking and reforming in slow, hypnotic waves. The heat is fierce, the air heavy with volcanic gases. Every movement in that molten lake is a message from deep below, from the mantle's molten pockets that feed it. Some volcanoes form at subduction zones, where one tectonic plate slides beneath another. Here, the sinking plate carries water and other materials into the mantle, lowering the melting point of the surrounding rock and generating magma. This magma is buoyant compared to the solid rock around it, and so it rises, sometimes pooling in chambers, sometimes forcing its way to the surface. These are the volcanoes of the Ring of Fire, strung like beads around the edges of the Pacific Ocean. They can be explosive, their eruptions sending ash high into the atmosphere, altering weather patterns for months or years. Other volcanoes are born far from plate boundaries, above what geologists call hotspots. These are places where plumes of unusually hot mantle material rise toward the surface, melting the rock above them. The Hawaiian Islands are one such chain, each formed by volcanic activity as the Pacific plate slowly moved over a stationary hotspot. The result is a trail of islands, each younger than the one before it, each built from the same deep source of heat. Volcanoes do more than release molten rock. They also bring up minerals and elements from deep within the earth, some of which will become part of the surface for the first time in millions or billions of years. Diamonds, for example, are formed under intense heat and pressure deep in the mantle, and some are carried upward by volcanic eruptions in a type of rock called kimberlite. In a way, volcanoes are couriers from the deep, delivering packages of minerals from the planet's hidden layers to its surface. The shapes of volcanoes, the nature of their eruptions, and even the sound they make are all influenced by what happens far below. A volcano fed by fluid basaltic magma may spill gentle rivers of lava that can flow for miles, glowing red as they cool. One fed by thicker, more viscous magma may trap gas until it explodes, sending rock and ash into the sky and reshaping its summit in seconds. Each volcano has its own character, its own voice, shaped by the chemistry and movement of its magma. For the people who live near them, volcanoes are both a blessing and a threat. The ash from eruptions can enrich soil, making it fertile for farming. The heat from geothermal activity can warm homes, generate electricity, or even prevent ice from forming on roads, as in parts of Iceland. But eruptions can also destroy towns, alter landscapes, and in the largest events change the climate. It is a relationship both intimate and precarious, living in the shadow of a furnace that can be quiet for decades and then, without warning, flare to life. Volcanoes also have a role in the planet's long-term balance. Over millions of years, they release carbon dioxide from the mantle into the atmosphere. This carbon can be captured again through the weathering of rocks, completing a slow cycle that helps regulate Earth's climate. It is another reminder that the surface and the deep interior are not separate worlds, but parts of a single, interconnected system. If you could follow the path of the magma feeding a volcano like Nyiragongo, you would descend through layers of cooling rock into a reservoir where molten material waits under immense pressure. Below that, you might find a narrow channel leading into the mantle itself, where the heat has been building for longer than human memory. The journey upward is not smooth. The magma stalls, changes composition, picks up crystals or gases, and only when conditions are right does it push through the final stretch to the surface. Standing near an active volcano can be humbling. The ground may tremble, a low sound rising from beneath your feet. The air may carry the sharp scent of sulphur. In the distance, you may see a column of steam and ash rising into the sky, marking the place where the deep earth has found a way to speak. It is the same voice that has built continents, shaped islands, and, at times, ended civilizations. The voice of fire from the hidden furnace. From here we will turn to follow the journey of magma itself, from the moment it forms in the mantle to its arrival at the surface. Along the way, we will see how magma chambers act as waiting rooms of fire, and how gases and minerals give each volcano its distinctive way of announcing itself to the world. If a volcano is the mouth of the earth, then magma is its unspoken thought, a message forming deep within, gathering shape and force before it reaches the surface. The journey of magma begins far below, in the mantle, where heat and pressure coax solid rock into a partially molten state. It is not a lake or river of liquid stone down there, but a mixture, crystals and melt interwoven, moving slowly through a hot and heavy world. Magma forms when something disturbs the balance of the mantle. In subduction zones, water carried down by a sinking plate lowers the melting point of the rock above, allowing it to melt more easily. At mid-ocean ridges, decompression melting takes over. As plates pull apart, the pressure decreases and the mantle can melt without any change in temperature. And in hot spots, plumes of unusually hot mantle rise toward the surface, melting the rock in their path. Each of these settings creates magma with its own distinct chemical signature, a kind of accent from the place it was born. Once formed, magma begins to rise. It does not rush upward like water through a pipe. Instead, it moves through cracks and spaces in the rock, pushed by its buoyancy and by the pressure of the molten material behind it. The journey can be slow, pausing for centuries in places where the rock above is strong enough to hold it back. When it stops, the magma often collects in reservoirs called magma chambers. A magma chamber is not an open cavern filled to the brim with lava, as you might see in fiction. It is more like a sponge of fractured rock saturated with molten material, a place where magma can gather, mix, and evolve. Here, crystals can form and settle, changing the composition of the remaining melt. Gases dissolved in the magma, water vapour, carbon dioxide, sulphur dioxide, are trapped under pressure, waiting for a chance to escape. The chemistry of the magma determines much of what will happen when it reaches the surface. Magma rich in silica is thick and sticky, trapping gases until the pressure becomes too great, leading to explosive eruptions. Magma low in silica is more fluid, allowing gases to escape more easily and producing gentler flows of lava. The minerals carried within it, the amount of water, the temperature, all of these are part of the volcano's voice, shaping the way it speaks when the time comes. Over time, the pressure in a magma chamber may build until the rock above can no longer contain it. The trigger could be an injection of new magma from deeper below, an earthquake that shifts the surrounding rock, or simply the steady accumulation of pressure as gases expand. When the barrier breaks, the magma finds a path upward through conduits and vents. As it rises, the pressure drops, and the dissolved gases begin to come out of solution, forming bubbles. In thick magma, these bubbles cannot escape easily. so they expand rapidly, shattering the melt into ash and pumice in an explosive burst. In more fluid magma, the gases can slip away gently, letting the molten rock pour out as lava that flows for miles. The surface is not the end of the journey, but a transformation. Magma becomes lava the moment it emerges into the open air or onto the seafloor. It begins to cool, to solidify, to lose the heat that carried it upward. Some flows harden into smooth, ropey patterns called pahoho. Others break into sharp, jagged chunks known as aaa. Ash can settle across the land for miles, burying fields and forests, or drift high into the atmosphere, where it filters sunlight and cools the climate for months or years. Not all magma reaches the surface. Some cools and solidifies underground, forming intrusive igneous rocks like granite. These hidden bodies of rock may someday be exposed by erosion, but for now they remain buried, silent witnesses to a journey that ended before it could break into the open. In Iceland, the path of magma is sometimes close enough to the surface that it can be tapped for heat. Boreholes drilled into geothermal areas draw up steam and hot water heated by shallow magma bodies. This heat powers turbines, warms homes, and even keeps roads free of ice in the winter. Here, the journey of magma is diverted into a partnership with human life, the deep earth lending its warmth to the surface. To imagine the full path of magma is to trace a line from the deep mantle, through channels and chambers, up narrow conduits, and finally into the open sky. It is a path shaped by heat, pressure, chemistry, and time. Sometimes the journey takes centuries, sometimes it happens in a matter of weeks or months. But whether it ends in a quiet lava flow or a towering eruption, it is always part of the same deep cycle, the constant exchange between the hidden furnace and the world above. When you look at a volcano, active or long extinct, you are seeing the final chapter of this journey. The slopes, the crater, the cooled lava flows are all records of past magmas, each with its own story. And beneath your feet, even now, other stories are forming, molten and unseen, preparing for a journey that may not reach its end until long after we're gone. From here, our exploration will move beyond fire to the invisible shield that surrounds the planet, the magnetic field born in the molten depths, guiding life and protecting Earth from the solar wind. It is a force as silent as gravity, yet its presence shapes the world in ways we're only beginning to understand. If you were to think of the Earth as a home, it would be a very old one, built from the dust and fragments left behind when the sun and planets formed. The walls are solid, the roof is broad and sheltering, and deep within there is a kitchen. But this kitchen is not like any we know. Its oven has been on for more than 4.5 billion years, and it has never cooled enough to stop cooking. The heat it produces flows outward, shaping mountains, stirring oceans of molten metal, and setting the continents in motion. The sources of this heat are not obvious to us on the surface. We feel only the thinnest breath of it when we walk on sun-warmed stones or soak in a hot spring. But far below, 3 great fires feed the planet's warmth, each burning in its own way. The first is the heat left over from Earth's birth. When our planet formed, countless pieces of rock and metal collided and merged, each impact releasing enormous amounts of energy. That energy, trapped as heat, melted much of the young Earth, allowing heavy metals to sink toward the centre, while lighter materials floated upward. This process, called planetary differentiation, released even more heat as materials rearranged themselves. Though billions of years have passed, some of that original warmth still lingers deep inside, like embers under layers of ash. The second fire comes from the slow decay of radioactive elements in the Earth's interior. Isotopes of uranium, thorium, and potassium are scattered through the mantle and crust, each one unstable in a way that makes it shed energy over time. The particles they release collide with surrounding atoms, warming the rock around them. This is not a quick blaze, but a patient, steady source of heat, a slow rain of energy that has been falling since the planet's earliest days and will continue for billions more. The third fire is less ancient, yet no less important. As the Earth's inner core slowly grows, iron crystals form from the molten metal of the outer core. When these crystals take shape, they release latent heat, energy stored in the liquid state, and that heat rises into the layers above. This process also releases lighter elements into the molten outer core, helping drive the convection currents that create our magnetic field. The growth of the inner core is like adding a new log to the fire every day, keeping the furnace burning steadily. Together, these three sources keep the deep earth hot enough for the mantle to convect, for magma to form, and for the outer core to remain molten. Without them, the planet would eventually fall silent inside. The magnetic field would fade, plate tectonics would stop, and the surface would grow geologically still, much like the moon. We measure the flow of this heat, called the geothermal gradient, by sinking sensors into mines and boreholes. On average, the temperature rises about 25 to 30 degrees Celsius for every kilometre you go down through the crust, though this rate changes depending on where you are. Near volcanic regions, the increase is much steeper, a sign that heat is close to the surface. In stable continental interiors, the gradient is gentler, the heat trapped deeper below. The total heat flowing out of the Earth is estimated at about 47 terawatts, an amount of power thousands of times greater than all human energy use combined. Yet because it is spread so thinly across the planet's surface, we hardly notice it in daily life. Only in special places, geothermal springs, volcanic vents, deep mines, do we feel it directly. It is strange to think that the continents drifting, the earthquakes shaking, the volcanoes erupting, are all in some way powered by this invisible warmth. The crust may seem solid and cool, but it is the outer skin of a world that is still, in its own way, alive with heat. If you imagine the Earth as a giant pot left simmering on a stove, you can picture how this heat moves. The mantle is the thick stew inside, slowly turning over in great loops of convection. The heat from below keeps the stew moving, carrying materials from the deep toward the surface and drawing cooler material back down. Without this movement, the stew would settle, and the flavours, in the Earth's case the minerals, the crust, the oceans and the continents, would never mix. And yet, unlike a pot on a kitchen stove, the Earth has no cook tending it, no hand turning the heat up or down. The fires simply burn at the rate they can, balancing themselves over eons. Radioactive decay slows as isotopes are used up. The inner core grows, but only at a pace the outer core allows. The leftover heat from formation fades, but it does so slowly that it still drives processes begun billions of years ago. This long, slow balance is why the Earth has remained geologically active for so much of its history, while smaller planets and moons have cooled and grown still. Mars, for instance, lost much of its internal heat early, and its surface bears the marks of ancient volcanoes that no longer erupt. Mercury, even smaller, has been cold and quiet for most of its life. The Earth's size and composition give it the ability to hold on to its warmth, and that warmth has shaped every chapter of its story. From here, our journey will shift from the deep sources of heat to the ways we've learned to borrow it for our own use, tapping into the steady warmth of the planet not only for power, but for comfort and survival. When you think of the energy we use each day, the lights in our homes, the warmth in winter, the hum of machines, most of it comes from fuels we have to dig, drill or grow. But there is another source, older than any mine or forest, one that has been flowing beneath our feet since the Earth's first days. It is the steady heat of the planet itself, rising from the mantle and crust, waiting quietly in certain places for us to notice it. In some regions, this heat lies close to the surface, trapped in reservoirs of hot water and steam. Where volcanic activity is recent, or where the crust is thin, the geothermal gradient is steep, and the deep warmth is only a short distance away. These are the places where tapping into the Earth's heat becomes not only possible, but practical, a direct connection between human life and the planet's internal fires. Iceland is perhaps the most famous example. Straddling the mid-Atlantic ridge, it is a land born of volcanic activity, still rising and reshaping itself from eruptions and fissures. Beneath its surface, magma-heated water and steam collect in underground aquifers. Wells drilled into these reservoirs bring up water that can be used directly to heat homes, schools, and greenhouses. In Reykjavik, nearly every building is warmed this way. The water flows through radiators in winter, keeping rooms comfortable even when snow falls outside. It also feeds public swimming pools, open year-round, their water steaming under the pale winter sun. The heat is not just for comfort. In Iceland's power plants, geothermal steam spins turbines, generating electricity without burning fuel or producing smoke. Some of the hot water is even piped beneath sidewalks and streets, melting snow and ice before it can pile up. It is a kind of partnership, the deep earth lending its warmth, and the people shaping it into a daily resource. Other countries also draw on geothermal energy, though in different ways. In Kenya's Rift Valley, geothermal plants use the heat from volcanic systems to supply electricity to the grid, helping power cities and industries. In New Zealand, geothermal steam has long been used both for electricity and for local heating, particularly in the volcanic plateau of the North Island. In the United States, parts of California, Nevada, and Alaska make use of geothermal power, with plants operating in landscapes shaped by the same tectonic forces we've been following. The scale of this energy is vast, though unevenly distributed. In theory, geothermal heat is nearly limitless on human timescales. The slow cooling of the planet will take billions of years, but in practice we can only reach it in certain locations, where geology brings the warmth close enough to tap. Even so, the International Renewable Energy Agency estimates that geothermal power could meet a significant portion of the world's needs if developed carefully and sustainably. Using geothermal energy has a particular kind of elegance. It produces almost no greenhouse gases. It does not require vast amounts of land like some other renewable sources. Once a system is in place, it can provide power and heat around the clock, unaffected by the weather or the time of day. It is in many ways the quietest of energies, a constant, steady breath of warmth from the deep earth. Of course, it is not without challenges. Overuse of a geothermal field can cause pressure to drop, reducing the output of wells. The chemistry of the hot water can corrode pipes or leave mineral deposits that need to be managed. And while most geothermal systems are stable, there are cases where drilling has triggered small earthquakes, reminding us that tapping into the deep is not without consequences. Even so, the relationship is a remarkable one. We're used to thinking of the Earth's deep heat as something dangerous, the force behind eruptions, the molten core of disasters. But here it becomes something sustaining, almost domestic. It is the same warmth that melts rock into magma, but softened into the steam that turns a turbine, the hot water that fills a bathtub on a winter night. If you have ever stepped into a geothermal spring, you have felt this connection directly. The water may emerge from the ground too hot to touch, cooled only as it flows across the land. The air around it shimmers with steam. In those moments you are sharing a sensation with the deep earth itself, the same heat that has been circulating far below for longer than life has existed. The idea that we can borrow warmth from the deep, without exhausting it, is a reminder of how much of the planet's story is about balance. We take only what rises naturally, and the fires below continue their slow work, unchanged by our presence. It is not extraction in the usual sense. It is more like opening a window to let in the heat from a stove that is already on. In the next part of our journey, we will see how this same deep heat, plays a role in shaping the atmosphere and climate over millions of years, not through warmth alone, but through the slow exchange of gases between the mantle, the crust, and the air we breathe. The deep Earth does not just warm us, it helps keep the surface in balance, holding the climate within the narrow band where life can flourish. If you could step back far enough to see not just the surface of the Earth, but the cycles that keep it livable, you would notice something surprising. The climate, the long-term pattern of temperature, rainfall, and habitability, is not just set by the sun, the oceans, or the air. It is also shaped by the quiet interplay between stone and fire, between the hard crust we walk on and the molten depths below. This partnership has been running for hundreds of millions of years, and it has kept the Earth within a narrow range of conditions where liquid water can persist and life can endure. One of the key players in this balance is the carbon silicate cycle. It works so slowly that no one alive will ever see it complete a single round, yet over geological time it is one of the planet's most reliable regulators. The cycle begins with volcanic activity, the fire in our equation. Volcanoes, whether at subduction zones, mid-ocean ridges or hotspots, release carbon dioxide from the mantle into the atmosphere. This is carbon that has been locked away for millions of years, carried down into the Earth by subducting crust and recycled through the mantle's heat. Once in the atmosphere, this carbon dioxide mixes with rainwater to form a weak acid. When that rain falls on land, it reacts with the minerals in rocks, especially silicates. This chemical weathering slowly breaks down the rock, drawing carbon out of the atmosphere and carrying it in dissolved form into rivers and eventually to the ocean. There, the carbon is used by marine organisms to build shells and skeletons of calcium carbonate. When these organisms die, their remains sink to the sea floor, where they are buried and eventually turned into limestone. Over millions of years, tectonic processes carry that carbon-bearing rock back into the mantle through subduction. Heat and pressure break it down, releasing the carbon dioxide again through volcanic eruptions. The loop closes, and the cycle begins anew. It is a planetary breathing, a slow inhale of carbon into rock, a slow exhale back into the air. This process acts like a thermostat for the climate. If volcanic activity releases more carbon dioxide than usual, the planet warms, increasing rainfall and speeding up chemical weathering. The faster weathering removes carbon dioxide from the atmosphere, cooling the planet back down. If carbon dioxide levels drop too low, the planet cools, rainfall slows, and weathering decreases, allowing volcanic emissions to gradually restore the balance. The system is not perfect, and it works on timescales of hundreds of thousands to millions of years, but it is one of the reasons Earth has remained habitable, while other planets have swung to extremes. Mars, for example, may once have had a similar cycle, but as its internal heat faded and tectonic activity stopped, the process broke down. Carbon dioxide was no longer recycled from rock to air and back again. The atmosphere thinned, the surface cooled, and liquid water vanished. Venus, on the other hand, seems to have lost the balancing effect of weathering. With no oceans to draw down carbon dioxide, volcanic gases built up unchecked, driving a runaway greenhouse effect that turned the planet into the hottest world in the solar system. On Earth, the carbon silicate cycle has helped the planet recover from extremes. During the snowball Earth periods hundreds of millions of years ago, when ice sheets may have reached the equator, volcanic carbon dioxide slowly built up in the atmosphere because weathering had nearly stopped under the ice. Over millions of years, this greenhouse gas warmed the planet enough to melt the ice, allowing life to expand again. In the opposite direction, when the planet has overheated, increased rainfall and faster weathering have drawn down carbon dioxide, easing the heat. What makes this balance remarkable is that it depends on both the stone and the fire. Without volcanism, the carbon locked in rocks would never return to the atmosphere, and the planet would eventually freeze. Without weathering, volcanic carbon dioxide would build up endlessly, turning, Earth into another Venus. It is a conversation between the deep Earth and the surface, one that moves too slowly for us to hear in real time, but has been shaping our world for billions of years. Even today, the carbon silicate cycle is running quietly in the background. Every volcanic eruption releases a little carbon dioxide into the air. Every mountain stream carries traces of dissolved minerals toward the sea. Every limestone cliff holds the remains of ancient marine life, carbon locked away until tectonics calls it back into the mantle. We notice the short-term changes, a hot summer, a cold winter, but beneath them lies this ancient rhythm, patient and deliberate. It is humbling to think that the rocks beneath our feet and the molten layers far below are not just the stage for life, but active participants in its story. The balance they maintain has made it possible for forests to grow, for oceans to stay liquid, for human history to unfold in a narrow band of comfort. In the next part of our journey, we will leave the slow cycles of carbon and stone behind and begin exploring the invisible shield that protects all this, the magnetic field generated in the deep core, guiding life and shielding the surface from the solar wind. It is a reminder that the Earth's heart is not only warm, but magnetic, and that even the forces we cannot see are part of what makes this planet a home. Far above your head, beyond the highest clouds and the reach of weather, the Earth is wearing a cloak. You cannot see it. You cannot touch it. And yet, without it, the surface would be a very different place, harsher, emptier, stripped of much of the life that now fills it. This cloak is made not of fabric, but of force. It is the magnetic field, stretching tens of thousands of kilometers into space, shaping the very flow of charged particles that sweep past our planet. The story of this cloak begins far below, in the molten outer core. There, iron and nickel churn in slow, looping currents, driven by heat escaping from the inner core and by the planet's rotation. Moving metal generates magnetic fields, and when those motions are vast enough, the fields merge and align into something much larger, a planetary-scale dynamo. The result is a magnetic field that emerges near the South Pole, loops through space and re-enters near the North Pole, forming an invisible shield known as the magnetosphere. Out in space, the sun is constantly sending out a stream of charged particles called the solar wind. These particles move quickly, carrying their own magnetic field, and when they meet the Earth's magnetosphere, they are deflected around it. Instead of colliding directly with the atmosphere, most of them are swept to the side like leaves caught in a stream that splits around a rock. Without this deflection, the solar wind would strip away the upper layers of our atmosphere over time, as it has on Mars. The magnetosphere is not a perfect bubble. Some particles slip through, especially near the polar regions where the field lines bend down into the atmosphere. Here, the invisible curtain becomes visible in one of the most beautiful phenomena the planet offers, the auroras. If you have ever stood beneath an aurora, you will know how difficult it is to believe that what you're seeing is the result of collisions between tiny particles. The colours, green, violet, red, ripple and curl, forming arcs and curtains that sway as if stirred by a silent wind. These lights are born when charged particles from the sun spiral down along magnetic field lines and collide with atoms in the upper atmosphere. Oxygen glows green or red, nitrogen produces shades of blue and violet, and together they paint the night sky in shifting, living patterns. The auroras are reminders that the magnetic field is not static. Solar storms, bursts of energy and particles from the sun, can cause sudden, vivid displays, sometimes far from the poles. They can also disturb the magnetic field enough to affect satellites, navigation systems, and even power grids on the ground. In this way, the magnetic cloak is not just a shield, but a participant in a constant conversation with the sun, a conversation we can see, measure, and sometimes feel. Though we rely on it, the magnetic field is not entirely stable. Over geological time, it has reversed its polarity many times, with the north and south magnetic poles swapping places. These reversals are recorded in the patterns of magnetized minerals on the seafloor, forming stripes on either side of mid-ocean ridges. The process is slow on human timescales, taking thousands of years, but it is a reminder that the cloak is alive in its own way, shifting and changing as the currents in the outer core evolve. Even without reversals, the field is always in motion. The magnetic poles wander, drifting across the surface at speeds that can reach tens of kilometers per year. The strength of the field waxes and wanes, though it remains strong enough to hold back most of the solar wind. In some regions, such as the South Atlantic anomaly, the field is weaker, allowing more radiation to reach satellites passing overhead. These are details we only began to understand in the last century, but the field itself has been here for billions of years, guarding the thin layer of air and water that makes Earth habitable. If you could see the magnetosphere from space, it would not look like a perfect sphere. On the side facing the Sun, it is compressed by the force of the solar wind, while on the far side it stretches into a long tail, sometimes millions of kilometers long. Inside this space, charged particles are trapped in belts that loop around the planet, moving in paths defined by the field. Here, the cloak is more like a layered shield, with regions that deflect, trap, or channel particles depending on their energy and direction. For the creatures on the surface, this shield is more than a barrier, so it's also a guide. Some species can sense the magnetic field directly, using it as a compass for migration. In the next session, we will meet sea turtles, birds, and even sharks that can feel the pull of this invisible curtain, navigating oceans and continents as if they could see lines in the air. For them, the magnetic field is not just a silent protector in the sky. It is part of the map of the world itself. If the magnetic field is invisible to us, it is not invisible to everyone. Across the animal kingdom, there are species that can sense it as clearly as we see sunlight or feel the wind. For them, the Earth's magnetic cloak is not just a shield above the sky. It is part of the landscape, a quiet pattern running through the world, guiding their movements across seas, mountains, and continents. Sea turtles are among the most remarkable of these travellers. A hatchling emerging from its nest on a beach has never seen the open ocean, yet it will set off on a journey of thousands of kilometres, circling entire ocean basins before returning years later to the same stretch of sand where it was born. Research suggests that sea turtles imprint on the unique magnetic signature of their birthplace, a combination of field strength and angle that is like a hidden address in the ocean. Even decades later, that address is stored in their senses, drawing them home across currents and storms. Migratory birds carry their own magnetic maps. Some species can detect the inclination of the field lines, the angle at which they meet the Earth's surface, and use this to tell whether they are closer to the poles or the equator. Others appear to sense the field's intensity, giving them another layer of information about where they are. The exact mechanism is still a mystery, but experiments suggest it may involve specialized molecules in their eyes that respond to magnetic fields, allowing birds to see the field as a faint pattern overlaid on their vision. When night falls and the stars are hidden by clouds, the magnetic field still points the way. Even the oceans hold magnetic navigators. Sharks, rays, and certain fish are equipped with tiny gel-filled organs called the ampullae of Lorenzini, which can detect electric fields, and because moving through a magnetic field can induce tiny electric currents, these animals can sense the Earth's magnetism as well. For a shark, this sense may help in long migrations, in finding hunting grounds, or in navigating back to a familiar reef after roaming the open sea. To these creatures, the magnetic field is a stable thread running through their world. But it is not unchanging. Over centuries and millennia, the field drifts and shifts, and in rare events, it reverses entirely. If the cloak were to fade or reverse, how would they adapt? The geological record shows that reversals have happened many times, with no clear evidence of mass extinctions tied to them. This suggests that life is resilient, capable of adjusting even when the invisible lines of its map are redrawn. Some animals may rely on multiple cues, the sun, the stars, currents, scents, so that if one guide falters, another can take its place. For humans, the idea of losing the magnetic field's protection is more troubling. Without it, the solar wind could gradually erode the atmosphere, much as it did on Mars, though the process would take many millions of years. In the shorter term, the increase in charged particles reaching the surface could disrupt power grids, satellites, and navigation systems. Our own dependence on technology has made us more sensitive to changes in this field than our ancestors ever were. And yet most days the field does its work without drama. It holds back the stream of particles from the sun, channels some toward the poles to create auroras, and remains a quiet, constant presence for the creatures that can feel it. In this way, it is both an ancient protector and a living part of the present, linking the deep earth to the edge of space. Standing on a beach as the tide pulls back, you might imagine the journey of a sea turtle somewhere beyond the horizon, following a magnetic path you cannot see. Watching a flock of birds cross the autumn sky, you might wonder at the patterns they carry in their minds, maps written not on paper, but in the faint pull of the planet itself. Somewhere in the dark water, a shark may be tracing a route it learned long ago, guided by a signal that threads through every wave. The magnetic field does not announce itself, but for those who can hear it, it is a steady voice, speaking the same language now as it did 1,000,000 years ago. It is a reminder that the earth is more than the ground under our feet. It is also the space around us, the unseen lines of force that stretch into the night, holding the shape of our world in ways we're only beginning to understand. From here, our journey will move forward in time, into the Earth's far future, when continents meet again, when the heart of the planet cools, and when the cloak may change its shape or even fade. The story of the deep Earth is not finished, and in imagining what comes next, we can see more clearly how unusual and precious our present moment really is. If you could speed up time until millions of years passed in a single minute, the Earth would seem to breathe. Continents would drift like slow clouds across a sea of mantle. Oceans would open and close. Mountain ranges would rise and crumble. The shape of the world would be in constant motion, never fixed, never finished. And if you let that time-lapse play forward far enough, you would see something inevitable. The continents gathering again, merging into one vast supercontinent, just as they have done many times before. We know this not because we have seen it happen, but because the evidence lies in the rocks beneath our feet. The continents have united and separated in a repeating cycle, known as the supercontinent cycle, for more than 2 billion years. Pangaea was the most recent, breaking apart about 200 million years ago into the continents we know today. Before it came Rodinia, and before that, Nuna. Each was assembled by the slow collisions of drifting plates, and each eventually broke apart as heat and motion beneath the crust forced them to move again. Right now, the continents are still drifting. Africa is inching northward toward Europe, closing the Mediterranean Sea. Australia is moving steadily towards Southeast Asia. The Americas are sliding westward, carried by the plates spreading along the mid-Atlantic ridge. These motions are slow, only a few centimeters each year, but they are relentless. Over tens of millions of years, they add up to oceans disappearing and mountain ranges forming. In about 250 million years, these movements are expected to bring the continents back together. Geologists have proposed several possible scenarios for the next supercontinent. In one, called Pangaea Proxima, the Atlantic Ocean closes, pulling the Americas back toward Africa and Europe. In another, Orica, both the Atlantic and Pacific close, and the continents meet somewhere near the equator. There is even a scenario called Novopangia, in which the Pacific continues to shrink until all land meets around its rim. Whatever shape it takes, the formation of a new supercontinent will remake the planet's climate and ecosystems. Large land masses in the interior tend to be dry, because moist air from the oceans cannot easily reach them. Temperatures can swing widely between seasons, with scorching summers and freezing winters. Oceans too will be reshaped, changing the paths of currents that carry heat around the globe. Species will adapt, migrate, or vanish, just as they have in previous cycles. The very act of forming a supercontinent is both creative and destructive. As plates collide, they thrust up mountains like the Himalayas today. Volcanic arcs may form along the boundaries, releasing gases into the atmosphere. But the merging of continents also means the closure of seas, the loss of coastlines, and the disruption of habitats that once supported marine life. It is a reminder that the Earth's changes are not gentle on all scales. They create and erase in equal measure. And yet there is something steady about this vast rearrangement. It is not chaos, but the continuation of a rhythm older than complex life. The engine that moves the plates, the mantle's slow convection, is powered by the same deep heat we have been following since our journey began. As long as the mantle moves, the continents will not stay still. If you could stand on the shore of that future supercontinent, the land might stretch away in every direction, a single mass under a single sky. The mountains could be newly formed, their peaks sharp and raw, or they could be worn down into gentle hills by millions of years of rain and wind. The ocean you see might be an entirely new one, with currents no one today could name, and somewhere beneath your feet the plates would still be moving, beginning the slow process that will one day break this supercontinent apart again. Thinking about this distant future is a way of remembering that the Earth's story is not bound by our own timelines. The places we think of as permanent, the shapes of continents, the positions of oceans, are only temporary arrangements in a far longer play. The coastlines of our childhood maps will not last. The mountains we know will change. And someday, the lands will meet again, as they always have. From here, our journey will move further into the future, to a time when the deep engine itself begins to slow, when the heart of the planet cools and the magnetic shield fades. The continents may still move, but the cloak above us may no longer hold, and the Earth will have to face the sun without its most ancient protector. Deep below the continents and oceans, the Earth's heart is still beating. It is a slow, heavy pulse, the churning of molten iron in the outer core, the gradual growth of the solid inner core, the steady flow of heat toward the mantle. This movement powers the magnetic field that wraps around the planet. But like any heart, it will not beat forever. The inner core is growing, and as it does, the outer core is losing heat to the layers above. One day, far in the future, that transfer will slow, and the great currents in the outer core will weaken. The dynamo will falter, and the magnetic cloak will fade. It will not happen in our lifetimes, or in the lifetimes of any species alive today. The timescale is measured in billions of years. But when it comes, it will mark a profound shift in the Earth's story. Without the dynamo, the magnetic field will vanish, and the planet will face the sun without its most ancient shield. We have an example of what this can mean. Mars, once warm enough to support rivers and lakes, is now cold and dry. Geological evidence suggests that Mars once had its own magnetic field, powered by a molten core. But as the planet cooled more quickly than Earth, the convection in its core stopped. Without the shield, the solar wind began to strip away the atmosphere. Over millions of years, the air grew thin, water evaporated into space, and the surface became the desert we see today. Venus offers a different lesson. It too has no global magnetic field. Its dense atmosphere remains, not because of a shield, but because it is so thick and heavy that the solar wind cannot easily remove it. Yet without a protective field, high-energy particles from the sun constantly bombard the upper atmosphere, driving chemical reactions that may have helped trap carbon dioxide and fuel the runaway greenhouse effect. Venus is a reminder that without balance, heat and pressure can spiral far beyond the limits of habitability. For Earth, the loss of the magnetic field would not mean instant catastrophe. The atmosphere is thick enough that it would not vanish overnight. Life in the oceans would still be sheltered from radiation. But over millions of years, the constant stream of charged particles from the sun would slowly erode the upper atmosphere. Cosmic rays and solar storms would reach the surface more easily, making the planet harsher for life. Satellites would face more damage from radiation. Long-term climate patterns could shift as the atmosphere changed. The fading of the magnetic field would also change the most beautiful expressions of its presence. The auroras, those green and violet curtains in the polar skies, would grow faint, then vanish. Migratory animals that rely on the magnetic field might adapt to new cues, but their invisible maps would be redrawn forever. And yet, even without the shield, Earth's story would not end. The mantle would still convect, though more slowly. Plate tectonics might continue for a long time, reshaping continents and creating mountains. The carbon-silicate cycle could still regulate the climate on long timescales, though the increased erosion from solar wind might alter the balance. Life, if it still remained, would adapt as it has to every other change in Earth's history. The cooling of the core is not a sudden stop but a long fade. Even now the inner core is growing at only about 1 millimeter each year, releasing heat and lightening elements into the outer core. The dynamo is strong enough to hold back the solar wind for billions more years, but its eventual stillness is as much a part of the planet's life cycle as the drifting of continents or the rise and fall of oceans. In imagining this distant future, we're reminded of the delicate combination that makes Earth so unusual today. A warm heart, a moving mantle, a magnetic cloak, and a balance of atmosphere and climate that allows life to flourish. It is a combination born of chance and sustained by slow, patient processes deep below the surface, and it will not last forever. But perhaps that impermanence is part of its beauty. To know that the auroras are not eternal, that the shield we live under is a passing phase in a longer story, is to see them differently, as gifts of this particular moment in planetary time. Just as the continents will one day gather and part again, the cloak will one day fade, and the earth will face the sun bare. For now, though, the heart still beats, the field still flows, and the sky's secret curtain still dances when the night is clear. From here, we will take our final step, looking at why the Earth, with all these moving parts, is so rare among planets we know, and why this moment in its history is worth noticing, even as it passes quietly beneath our feet. If you were to line up all the planets we know, the 8 of our solar system, and the thousands we have discovered circling other stars, the Earth would not look extraordinary at first glance. It is not the biggest, it is not the smallest, it does not orbit the brightest star, or the dimmest, or the oldest. But to understand why it is rare, you have to look beneath the surface, into the parts we cannot see. What makes Earth unusual is not just its place in space, but the restless balance of forces deep inside it, and the way they work together to keep the surface alive. We have seen some of those pieces already. The molten outer core, moving in slow currents, creates a magnetic field that shields the atmosphere from the sun's charged winds. The mantle, circulating over millions of years, drives plate tectonics, reshaping the continents, building mountains, and recycling carbon between the surface and the deep. The crust, thin as the skin of an apple, holds oceans and life, while still being flexible enough to break, move, and heal over time. Above it all, the atmosphere stays thick enough to hold a warmth, thin enough to let sunlight through, and rich enough in oxygen to fuel complex life. Each of these elements can exist on other worlds, but rarely together and rarely in balance. Venus has a thick atmosphere but no magnetic field, and its surface bakes under a runaway greenhouse effect. Mars once had liquid water, but its small size allowed its core to cool quickly, shutting down its magnetic field and letting the solar wind strip its air away. Even among the hundreds of rocky exoplanets we have found, few show signs of having both plate tectonics and a magnetic shield, two features that on Earth work hand in hand to keep the climate stable over immense spans of time. Earth's restlessness is part of what makes it habitable. If the plates did not move, mountains would erode into plains, carbon would remain locked in rock, and the atmosphere would slowly thin or thicken without regulation. If the magnetic field did not exist, the sun's wind would chip away at the air, and high-energy radiation would make the surface far less forgiving. If the deep heat were weaker, these systems would slow and the planet's cycles would falter. If the deep heat were stronger, the surface might be more volcanically active than life could tolerate. The balance we have now is not perfect, but it is rare. This combination is also temporary. It exists now because of the Earth's age, size, and history. The planet is old enough that its early chaos, constant bombardment, unstable crust, toxic atmosphere, has given way to stability, but young enough that its core is still hot and its plates still move. Too much time in either direction and the balance shifts. That is why our moment in the Earth's history is both fragile and extraordinary. It sits in a narrow band where the forces of fire, stone, water and air are all in motion and all in conversation with each other. Other worlds remind us how easily the balance can tip. Mercury, small and dense, still has a weak magnetic field, but its thin atmosphere offers no protection from the sun's glare. Titan, a moon of Saturn, has a thick atmosphere but no tectonics, and its surface is frozen under a haze of methane. Europa has a global ocean beneath its ice, kept liquid by tidal heating, but no land masses to cycle carbon between ocean and sky. Each of these worlds has a story worth telling, but none match Earth's mixture of moving plates, active core, and protective cloak. It is tempting to think of this balance as something designed for us, but the truth is the reverse. We are here because the balance existed first. Life emerged in the conditions Earth provided and then evolved to fit them. If the continents had been fixed, if the field had never formed, if the climate had wandered too far from stability, our planet might have been as lifeless as so many others. We are, in a sense, the expression of Earth's geology, the living surface of a restless world. This restlessness is not always comfortable. Earthquakes can shatter cities, volcanic eruptions can darken skies, and shifting climates can challenge life. But these same processes are the heartbeat of the planet, and without them, we would not be here to witness their beauty or endure their power. The same deep heat that feeds a volcano also drives the magnetic field. The same moving plates that trigger earthquakes also keep the air breathable over millions of years. So when we call Earth rare, we're not only talking about its place in the cosmos, we're speaking about the particular way it moves. We're acknowledging that the warm heart, the moving mantle, the drifting continents, and the invisible cloak are all part of one system, a system that has kept the planet alive through ice ages, asteroid impacts, and the slow march of time. In the next final part of our journey, we will let go of the future and the past and return to the present, to the surface under your feet, the air around you, and the quiet knowledge that you are living on a rare and restless world. The deep heat still flows, the plates still drift, the cloak still holds. And tonight, all of that is here with you, in the stillness between one heartbeat of the planet and the next. If you spend enough time thinking about Earth, you start to notice its contradictions. It is loud and violent, storms tearing at coastlines, volcanoes lifting new mountains into the air, earthquakes rearranging entire cities. And yet beneath all that movement is a patience so vast it feels like stillness. The surface may crack and roar, but deep down the planet moves to a rhythm that makes even the longest human lifetime seem like a blink. There is a comfort in that. We live in a world where the scale of change is often measured in news cycles, quarterly earnings, and school terms. A decade feels long, a century is almost unimaginable, and anything older than that belongs to the vague realm of history. But Earth is not hurried. It does not share our sense of urgency. The movement of its continents, the drifting of its magnetic field, the slow cooling of its core, these are measured in millions, even billions of years. If you could watch them in real time, you might think nothing was happening at all. And yet, over these vast spans, whole oceans are born and destroyed, mountain ranges rise and vanish, and climates shift in ways that shape the evolution of life. There is something deeply human about looking for reassurance in that slowness. We are fragile, temporary creatures. Our lives are full of beginnings and endings, of sudden turns we never saw coming. The idea that somewhere beneath our feet, in the rock and metal we will never touch, there is a steady, unbroken cycle that has been running since before the first cells formed in the sea. It is like discovering that the floor beneath your house is made not of wood but of solid ancient stone. Even when storms rattle the windows, the foundation holds. It is not that Earth is unchanging, far from it. The very stability we feel comes from movement, heat flowing from the core to the surface, minerals cycling from deep rock to shallow soil, oceans trading warmth with the sky. Change and stability, it turns out, are not opposites here. They are partners in the same long dance. The quiet is not the absence of noise, but the space that allows it to exist without chaos. If you've ever been near a forest in late summer, you know this feeling. On the surface, the air is alive with movement, insects tracing invisible paths, leaves flickering in the wind, birds darting between branches. But if you stand still long enough, you begin to sense the deeper layer, the weight of the trunks, the slow thickening of wood, the roots pressing into the soil. That same layering exists beneath us now. The frantic scurrying of our lives is like the rustle of leaves. The deep processes of the planet are the growth of the forest itself. Sometimes, when the ground trembles or a volcano paints the sky red, it is tempting to think the planet is waking up. But the truth is, it has never been asleep. These events are only small ripples in a sea of constant motion. Even the sudden, the catastrophic, is part of a pattern that stretches far beyond memory. The same forces that can bring down cities are also the ones that build the continents we stand on, that keep the magnetic field wrapped around us, that hold the balance of the oceans and sky. And so, there is comfort in knowing that while our own lives are measured in decades, Earth's heartbeat is measured in epochs. The tectonic plates will keep moving long after our calendars have turned to dust. The iron heart at the centre will keep spinning its magnetic shield while empires rise and fade. Even if we cannot feel it, the deep mantle will keep flowing, as it always has, carrying the heat of the planets, birth toward the crust in slow, unstoppable currents. When you think of it this way, the noise of human life, the rush, the tension, the constant reaching for what's next, begins to seem a little smaller, not unimportant, but lighter, less absolute. The ground beneath us is older than anything we can name, and it will go on after the last of our buildings have fallen. To live here is to be part of a story that began long before we arrived and will continue long after we're gone. That story is not written in years but in layers, of rock, of ice, of sediment at the bottom of the sea. It is told not in paragraphs but in the tilt of coastlines, the mineral seams in mountains, the fossil shells embedded in stone. If we could read it as easily as a book, we might find that our own time here is only a sentence or two. And yet, even the shortest sentence can matter if it belongs to the right story. So perhaps the gift Earth offers us is perspective, to remind us that stability does not mean stillness, and that change does not always mean loss. We are here for a little while, sharing the surface with rivers that carve their beds grain by grain, with winds that shape dunes over centuries, with glaciers that inch forward and retreat in rhythms far older than our species. The planet's slow work makes room for our quick lives. Tonight, as you rest, the deep engines of the Earth will keep turning. Magma will rise and cool far below your feet. The core will keep spinning, its magnetic field reaching out to catch the solar wind before it touches the sky. Rocks will shift imperceptibly along faults, storing energy for quakes that may not come for hundreds of years. None of it depends on our attention. None of it waits for our permission. And maybe that's the most reassuring thing of all. In a world where so much feels uncertain, where the future can seem like something fragile enough to shatter in a day, there is still this, a planet breathing slowly in the dark, holding both the quiet and the noise, and keeping its long rhythm while we sleep. The Earth does not rest, but it knows how to keep watch. Beneath its cool crust, heat flows like a slow breath, rising through stone, pooling in chambers of molten rock, drifting upward until it meets air and ocean. Even in the calmest night, far from volcanoes or shifting faults, the deep fire is there. Patient, contained, older than the oldest mountain you've ever seen. Think of it as a guardian's lantern. For more than 4 billion years, it has been burning quietly, lighting the inside of the planet. It forged the first continents, lifted islands from the sea, and melted paths for rivers to follow. Without it, the magnetic field would be gone, the plates would stand still, and the balance of air and ocean would unravel. It is both the threat and the protection, the destroyer and the maker. You live on a cradle of fire, and yet it feels steady beneath you. The same mantle. Plumes that feed volcanoes also feed life, sending minerals to the surface that will nourish soils for forests yet to grow. The same tectonic shifts that sometimes bring quakes also recycle the crust, keeping the planet's skin young enough to breathe with weather and water. The deep heat is not an enemy. It is the heartbeat of the world. Tonight, as you lie in your own small corner of this vast sphere, the planet will keep its quiet watch. Somewhere a volcano's lava lake will churn under a crust of black rock. Somewhere else a glacier will creep over bedrock, grinding it into new soil. The auroras will shimmer at the poles, tracing the invisible lines of a magnetic shield, spun from molten iron 2,000 miles beneath your feet. Oceans will shift with the pull of the moon. Tides will rise on one shore and fall on another, each movement counted in the patient mathematics of gravity and time. You are part of this watch, even if only as a witness. The iron in your blood was once part of the same cosmic dust that built the core. The oxygen in your lungs is here because the planet's surface has been stable enough for plants to weave it into the air over countless generations. Every breath you take is a quiet exchange with the rest of the living world, a signal that you are still here, still moving to the planet's rhythm. In the morning, the crust beneath you will be a fraction of a millimetre farther from the mantle's deepest heat. The continents will have shifted by an immeasurable fraction of an inch. A few more atoms will have traded places in the core's slow dance, keeping the magnetic shield alive. You will not notice any of it, but it will all have happened. The fire will keep burning, not in a rush, but with the calm certainty of something that has nowhere else to be. If you could hear the planet breathe, it might sound like the slow swell and retreat of waves. If you could feel its heartbeat, it might be the faintest thrum beneath the soles of your feet, carried up from the deep by stone and water. It has been there since before there was anyone to name it. It will be there long after our words have faded, and so, tonight, you can rest without asking the earth to pause. It will not. It will keep shifting, turning, flowing, watching. It will keep holding the thin skin of air that wraps around us, the water that moves between cloud and sea, the ground that holds the weight of our cities and the roots of our forests. You are safe in the care of a planet that knows how to endure. Close your eyes and imagine yourself not separate from it, but carried along with it. The turning of the planet is the rocking of your bed. The pull of gravity is the weight of a blanket. The hum of life around you is the sound of the mantle moving far below. Let the fire burn in its deep chambers. Let the oceans keep their tides. Let the air move in its long, slow circuits. Sleep now, little traveller on a planet that breathes fire. The world will keep its long vigil until you wake. And when you do, it will still be here, still turning, still burning, still holding you,